Okay, so in this video we'll do our first of a couple of examples of the spring model. The vibrational spring model this sort of has a million different names depending on where you're looking, I guess. But so we finished in the last video getting our model in order, and here it is in the box at the bottom there. So it's a homogeneous ODE, because I have a 0 on the, well, usually we said right-hand side, but I guess left-hand side in this case. And then on the right-hand side, of course, M, gamma, and K are all positive numbers, and they're all going to be, they're numbers, right? So, of course, to solve this is not going to be hard at all. This is not going to be the hard issue with these problems, but what is maybe sometimes the follow-up questions and what kinds of things do we want to know about these things. So let's try one. So here's our model. I'll copy it down on the next slide. But we'll do about 3-ish or so examples. So let me write down the verbiage first, and then we'll dissect it and put it line everybody up and everything. So here we go. So a ball weighing 4 pounds. Hangs from a 1-foot spring, causing it to elongate 3 inches. Okay. What else? So it says the damping force is 6 pounds. When the velocity is -3 feet per second. And okay, and we have one more sentence which says you will pull the ball down 6 feet and let it go. Okay, so this is the 3 sentences or so that describe the setup for the model, and of course describe how you set it into motion, which is that you're going to pull it down and let it go. Right, so we sort of, we have some understanding, of course, of what's going to happen. When I have a spring and I pull it down and I let it go, it bounces boing, 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 and if this is real life, it eventually sort of comes to rest back at the equilibrium state. But let's see what happens, I guess. So the question, of course, is going to be set up and solve an ODE to give you the displacement from equilibrium at time t. Right. So set up and solve. Even if it doesn't ask you to do this, you have to certainly do this before you can answer any follow-up questions. So set up and solve an ODE for the displacement at time t, which is u. Okay, so let's go. So our model is, of course, this that we just spent quite a bit of time getting happy with. Mu double prime plus gamma u prime plus ku equals 0. Okay, so obviously we're going to have to fill in what m, gamma, and k are, which we'll do in a minute. But of course, remember, this is an ODE, and in fact, it's a second-order ODE. And last time I checked, in order to actually fully solve a second-order ODE, we needed 2 initial conditions, one usually about the function, and one usually about the derivative of the function. Now, I didn't say a whole lot about this in the derivation, because this should hopefully be obvious now, that of course embedded in the word problem is going to be some sort of indicator of what's happening at time 0, or in other words, when you start this experiment, what are you doing to this spring? Well, that's the last sentence. So the last sentence says that in order to set this in motion, you're going to pull it down 6 and let it go. Now, of course, let it go probably means something like you're not hitting it, or you're not pushing it in either direction. You're just sort of releasing it, right? So I have to do a little bit of brain work here and say, oh, okay, you pull it down 6 feet. That means, of course, the initial position is 6. Remember, you keep having to remind yourself that we're in opposite land, right? So down 6 really means positive 6. So u of 0, remember u is displacement, so u of 0 should be 6. And I should also always be able to identify u prime of 0. So I should always be able to identify the initial displacement and also the initial velocity, right? Of course, velocity is the derivative of position. So u prime is something I should always be able to tell from the problem. In this case, let it go, I'm pretty sure means you give it no initial velocity. If it said something like you smack it up or down with some initial velocity or speed, then I would probably record that as my u prime. But in this case, let it go means I think just u prime is 0. Okay, so those are, obviously we know when I'm going to need those. I'm going to use those at the end in order to solve, right? Okay, but before that, I don't actually have my model all set yet. I need to know m, gamma, and k. All right. So let's see. Let me go back to the problem and do some more reading. So it says the ball weighs 4 pounds. Okay. So first of all, weight, right? Weight is pounds is a measurement of weight, and newtons is also a measurement of weight, if we're doing the metric system. So those are bad, or bad at least in the sense that that's not mass. So if I'm going to fill this guy in over here, I should probably just organize my thoughts first. Weight is, of course, a force, and it's mass times gravity. So in this case, it tells us we have 4 pounds. That's slugs times gravity, and in the pounds, the foot-pounds system, the g is 32. Okay, so if I do a little bit of division here, my mass is actually 1/8 of a slug, would be the units there. Okay, but more importantly, I know m. So m is 1/8 slugs. All right, so I know m. I'll fill that in a second. Gamma. Okay, so gamma is the damping constant, or the coefficient of damping, or the drag constant, or the drag. Okay, all these things mean the same thing. So for damping, or drag, or resistance, there should be some sentence or indication. Now, I should say, actually, I was reading some of the homework problems. Some of them simply have no sentence at all mentioning damping or drag or anything like that. So you should assume in those cases that gamma is 0. All right, so I'll emphasize that, right? That if you have no information about drag or damping, you should assume that it's being neglected. In other words, we're just going to assume it's 0. Now, in real life, that's impossible to have no drag or no damping, because everything that moves through something, unless you're in outer space, right, there's some drag. But, of course, and sometimes we like to solve problems to make our lives a little easier. We relax one of these things. So if you see no information about damping, assume gamma is 0. Okay. But I do see something about damping. It says, the force due to damping is 6 when the velocity is -3. Oh, well, remember, of course, when we did our derivation, I had that the damping force was negative gamma u prime. That was our notation. Oh, well, the force due to damping is 6 when the velocity is -3. Velocity, that's u prime, isn't it? Okay, so in a matter of just a very easy, quick moment here, I know that gamma is 2. Great. All right, and lastly, for k, here's where I'm going to do my mg over L. That's the formula that we derived towards the end of the video, of the last video. Well, great, because I know those things. M is 1/8, G is 32, and L That's how much does it elongate, is 3. Okay, so now I get to have a little bit of fun here. Why did you just get this problem wrong? And by you, of course, I mean me. So somebody have a keen eye and take a look back at the problem, and then you realize, in case you forgot, why you absolutely hate word problems. You're immediately reminded of the fact, oh my God, this is inches. Whereas the units for that we're working with are feet, right? Feet, seconds, pounds, those all go together. So I have to be in feet, right? All my units, pounds are measured in feet, so I have to be in feet. Okay, so here's where it's annoying, but I have to remind myself, oh, you know what? I probably don't actually really want to think about 3 inches as much as, raise my wig. 3 inches is, of course, a quarter of a foot. Okay, now I'm happy. I should say my math is happy anyway. So a quarter of a foot, that's the L, big L elongation. I should say, notice, we don't really use this. That's little L, that's the original amount, that's how long the actual spring is. We don't really use it, at least not in the model. It may come up in some of our questions later on, but for the most part, you're not really using that. So, I mean, it might be included in a problem. They may also not include it. That's fine. You don't really need it. And if you think about it, that kind of makes sense, right? You don't actually need to know how long the original spring is. You just need to know how it changes, right, or evolves, right? That's what this model's for anyway. Okay, I probably would like a number for this rather than just math. So I think on the top there, that's 4, and 4 divided by a fourth is 16. Okay, so K, if I can squeeze in a little circle there. So K is 16. All right, so that took, I don't know, 5 minutes, I suppose. So there's a little bit of potential there for things to go wrong, I guess. But with a little bit of thinking and just maybe a small little side problem or two, we officially have our model. So here we are. So I've got 1/8 U double prime and 2U prime and 16U equal 0. So I'll put a nice little box or something around that. So we successfully did one of the hardest parts, I guess, which is we translated from words into mathy stuff. And now we get to do the easy part, which is solve this. And easy because, of course, we know how to do these things. So I'm going to go to a fresh slide here. So just continuing here. So here's our ODE, and of course I think we want to solve it. Did I write that down right? 2 and 16, yep, okay. And U of 0 is 6, U prime of 0 equals 0. Okay, so that's our setup. So let's solve this. Now, of course, to do this, we're going to do our usual, which is to find the roots of the polynomial here. Now, just a little pro tip. I think most of the time we've been doing these problems, you've had a 1 in front of the U double prime, which of course makes it easier to factor and stuff like that. A lot of times, of course, we're not going to in these problems because the mass is not always just 1. But if you want to make your life easier, which I certainly do, you can always clear that out, right? If I don't want a 1/8, multiply everybody by 8, right? That'll clear out the 1/8 and just make it a 1. All right, so times 8, is that 48, 128? Okay, I think that's right. Okay, so now I'm ready for quadratic formula, I'm pretty sure. I could try to factor this, but, well, okay, I'm not super thrilled or excited about that. So I'm probably 9 times out of 10 going to go right to quadratic formula, just unless I see that it factors nicely, but I don't necessarily see that here. So let's go to the quadratic formula, which would say opposite of b plus or minus b squared minus 4ac all over 2a. Okay, so of course you got to do the math under that square root sign. Believe it or not, that actually turns out to be, well, here, I'll jot it down. So 16, so if you do 16 squared and then minus 4 times 128, you actually get negative 16 squared. It's actually negative 256. So I'll write that down. .256 is 16 squared, though. All right, that's a coincidence. Well, somewhat. I mean, I sort of rigged this one, but you're not always going to get that, of course. But in this case, sure, nice, I guess. So let's see, what do I end up with? So I get negative 16. So that under the square root is 16 squared. But since it's negative, of course, when I bring it out of the square root of 256 is 16. But since it's negative, it's I. All right, so I'm pretty sure I end up with, what is that, negative 8 plus or minus 8 I. All right, so maybe not my favorite solution, I guess, in the world, but there it is. So, of course, we got complex roots. I don't want to spoil the surprise, but of course, we know complex roots means we're going to have sine and cosine in our answer. Well, let's pause for a moment and realize, well, of course you're going to have sine and cosine in your answer. It's a spring. What does a spring do? It oscillates up and down. Who goes up and down? Sine and cosine go up and down. So, I mean, it shouldn't be that much of a surprise. Now, we will look at an example where we don't actually get trig out of this, and we'll talk a little bit about what that means. But most of these problems, right, since it's a vibration up and down, trig will be in your future for most of them. Okay, so let's write down our answer here. Again, it's also a coincidence that those are the same. But all right, so we know that then our two solutions, or our general solution, U. So U of t is, if we don't already have this one memorized, C1, so it's e to the negative, remember that's A, and that's B. I think that's what the letters we were using. So e to the negative 8t, cosine of bt, and c2 e to the negative 8t sine of bt. Okay, so that's my general solution, but of course I have initial values to plug in, so I can do that and get answers for what these things might be. So if I use my initial conditions, so first, of course, I should get 6 when I plug in 0. Remind yourself, of course, when you plug in 0, sine of 0 is 0, so that's going to be all 0 over there on the right. That's all 0. But cosine of 0 and cosine of 0 is 1, and e to the 0 is 1, so actually you just get that 6 is C1. Well, that was easy enough. All right, so we're halfway there. 6 e to the negative 8t cos at a2 e sine of at. Okay, so we use the first fact. Let's use the second one. That'll probably tell us what C2 is. So for that, of course, I'm going to take the derivative. Ugh. Okay, so this is where this is a little unpleasant, I suppose. But all right, let's be brave here. So u prime, I need the derivative, because I could have to plug 0 in and see that I get 0. So unfortunately, I have to do the chain rule here in order to get the derivative of these. I'm sorry, the product rule to get the derivative of these two things. So all right, I guess let's do it. So if I do the product rule here, so I do the derivative of the first, let's say I get negative 48 e to the negative 8t times cos. And then when I do the derivative of the other piece, I get minus. I'm going to just sort of cheat here and say you're going to get something with sine. Why am I not even caring about that? Because in a second I'm going to plug 0 in, and all the terms that have sine are going to end up being 0. All right, so some stuff and then a sine, which when I plug it in is going to be 0. Second piece, I had to do the product rule here as well. Again, when I do the derivative of the first, I'm going to be multiplying by sine. So I'm going to have stuff, sine. Don't care. But the term I do care about is if I do c2 e to the negative 8t. Now if you do the derivative of sine of 8t, I get 8 cos 8t. Sorry, squeeze that in there. Okay, be a little more careful than me if you want. but I'm just trying to get through this problem. So now if I plug in 0, so let's do this now. So I plug in 0 and I'm supposed to get 0. So I get 0 when I plug in 0. When I plug in 0 to this is 1. This is 1. So you're going to get negative 48. When I plug in 0 to this, it's 0. That's 0. Anything with a sign is going to be 0. Okay, but now this last term, let's see. So when I plug in 0, that's 1. That's an 8. That's 1. So I think that's 8 times C2. Okay, so if I put all the pieces together, I just end up with 48 equals 8 C2, and so 6 is C2, which I keep saying it's a coincidence, but it is, right? Maybe not a coincidence in the sense that this was totally symmetric, that these two are also symmetric. In other words, I get 6 for both of them. Maybe that's not all that surprising, but that also won't always happen. But great. For the first example that we did, I'm not exactly upset that that happened. Okay, so we get our C1 and C2, and so we have our solution. I'm just going to write it on the next slide, but I probably can write it down here at the bottom with the celebratory we did it. So the solution is u of t, and we got C1 was 6, e to the negative 8t cos 8t, and C2 actually also turned out to be 6, and sine of 8t. Okay. Okay, so that's pretty exciting, I guess, that we got our first, we're able to solve our first modeling problem. And of course, remember, this is u, so this is displacement from equilibrium. Okay, so I feel like, we'd be bad people if we didn't have a little bit of curiosity about, well, does this make sense? I don't even know. Let me graph this. So I'm going to do a sketch, at least. I'll sketch you a graph of what this looks like. I'm not even going to punch this into a calculator. You can if you want to. So if you want to, punch this into a calculator and hit graph. But I promise your graph is going to more or less look like what I'm about to draw. So you don't have to be that fussy about making it perfect and to scale and all of that. But let's just take a look. So let's look at some graphs. Just for curiosity. And it's going to lead to some questions that we might have. So if you want to do, you can do a graph of u, because of course that would be me just punching that into a calculator, like I said, or having a little bit of intuition about what this might look like. Okay, so this is a graph of u of t versus t, or over time. All right, well, at time 0, we already knew that at time 0, I'm supposed to be at 6. Oops. Also, if I actually plugged in time 0, I'm pretty sure you get 6. So I think this is going to start up here at 6. Now, sine and cosine are waves, and even when you have them added together like this, sine and cosine are still just a wave that basically looks like a sine or a cosine wave. It's not perfect. It's not exactly, a starting point at the top and then right down and things like that. But anytime you see sine and cosine, if you just draw the usual kind of wave thing, you can't really go wrong. So don't draw this yet, right? But it's not this. I would say that either from your intuition, I'll say this is the first example we're doing here is pretty much real life, in terms of our parameters and setup and all of this. A spring, when you do what we just did to it, right? We said, okay, what did I say? We stretched it down. Is that what we did? We pulled it down and then we let it go. The spring doesn't do this. It doesn't. What should, of course, happen over time? It doesn't just keep bounding back and forth equally high and low like I just sketched. Of course we know what happens is that it vibrates or bounces wildly at first, but as time goes on, those bounces are getting shorter and shorter. In other words, I'm not moving up and down quite as much. So I think if I just asked you without doing any math to draw a graph of what a spring does, I don't know, I would probably say you should probably be drawing something more like this. And indeed, that is exactly the graph. Well, by exactly, I mean this is at least the right shape of the graph that you would get if you punch that into your calculator. Because of course what's happening, right, is that eventually, while this is in theory going on forever, as time goes to infinity, it's still oscillating. But e to the negative 8t, oh my goodness, when t is 1, e to the negative 8 is like 0.00000001. So it's going to kill this very, very quickly. All right? Okay, and the reason for that is that we have a high amount of damping. So 2 is a pretty high number for a damping constant, as we will see as we go through this. Right? So this is allowed to oscillate and bounce. However, it's very much being dampened or drag. The drag is very high. So this is going to slow the bouncing down pretty darn quick, and it's going to sort of stomp it out, so to speak. Okay. Now this is a graph of displacement. So remind yourself, of course, u is displacement. Right. So I think that's fine, but somebody else might say, but that's not the spring. The spring is not u, and that's correct. U is the displacement of the spring from equilibrium. So that's why, of course, this graph is focused on 0. But what is the spring itself? If I was going to try to sort of think about what is the spring actually doing, the spring is doing the opposite of this, or you could say it's doing the upside down of this, I guess, right? Because remember, of course, u is displacement, so positive u's mean the spring is actually down, and negative u's mean the spring is actually up. So I don't think you should do this necessarily, but I'll at least do one for you. I mean, I think displacement is plenty. But if you were curious or trying to present this to someone who didn't really understand what displacement was, you could make a graph of displacement, but you could also make a graph of the spring itself. And it is quite simply basically the upside down, right? The upside down version of this graph, right? So it starts, the spring has been pulled down. So I guess I could try to sort of do that's the ceiling. Did I spell that right? Ceiling? I don't know. Okay. That's the ceiling. And of course the spring is attached to the ceiling. And when I get started, I pull the spring way down. From equilibrium. And what happens? The spring, when I pull this is literally me pulling the spring. So I pull the spring down from its equilibrium, and I let it go. So of course what happens? Well, it does exactly the same shape that I have over here, but of course, when I view it this way, sorry, I should put that line in first. Not my best art. Okay. So of course I pull the spring down, I let it go, it shoots way up, right? Way up above equilibrium. And then elasticity takes over here, I guess, and it starts to bounce back down again. And then elasticity, the spring force pulls it up over again, and then down. But of course, at this point, I'm just barely oscillating above equilibrium, right? So this is, of course, equilibrium. I guess I could say L for equilibrium, right? That's the equilibrium elongation. That's L plus 6, or L minus 6, I guess, if I'm doing it below. Right? That's me pulling it down 6 units. Oh, we know how much L is, sorry. I didn't mean to. L is a quarter. Okay, well that's kind of awkward. I'm not going to put a quarter on there, but technically yes, that's a quarter, which is not very big, right? I mean, I'm not doing a whole lot, but I have no idea where the ceiling is, right? So I mean, I'm not really trying to necessarily say, is this going to smack the ceiling? The original, well, anyway, okay, I don't want to get too fancy with this. But the idea is, of course, since the spring is the opposite, or our sign is flipped for u, the path of the spring, if I was trying to say, so what does the spring do? Well, you pull it down, and then you let it go, and you see it, of course, doing this. Okay, so apart from saying, well, it's good that this matches our notion of what we, as humans, know a spring should do, maybe, if we have a little bit of intellectual curiosity, we might say, there might be a famous moment or two in the journey of this spring that I want to maybe unpack a little bit. Now, one famous moment, I suppose, and you could do this on either graph. Since I'm mostly not going to even draw this one over here, over here, the spring path, let me come back to displacement, because I think most of the time we're just going to work with this one. But there might be a famous moment or two. So we're going to unpack these moments. So let's call that moment A, and let's call that moment B. There's probably some other famous ones along the path here, but those are probably the most famous, I guess. And by famous, I mean, something interesting happens at these points, A and B there. So, of course, at point A is the first time the spring comes back to equilibrium, right? Of course, that's on here too, right? These points are on both of these graphs, right? So A would be the first time it comes back to equilibrium. Well, I might want to know about that, because maybe something's happening, right? Maybe in fact I'm mostly only interested in this portion of the experiment. Like, I pull the spring down and I just want to see how long is it going to take for it to snap back up to equilibrium, right? So A might be an important moment. B feels like an important moment because it is where, looking at our graph, if I'm looking at the U graph, this is the lowest, or I should say on my graph it's the lowest. Of course, since I'm upside down here, it is also the highest moment. It is where the spring comes closest to the ceiling. That would be at moment B. So those seem a little noteworthy, right? I mean, these other moments over here, I don't really care too much about those, I don't think. So let's ask and answer those questions, right? What about moment A and what about moment B? And the book will ask you to do some things like this too. So I want to mostly just show you that you need a little bit of algebra / trig and memory here to do this. So let's do that. I'm just going to get a clean slide here. So part A, I'll do capital A since we're answering the question about point A. Might be a question like this. When does the ball, or whatever it is, the mass, first return to equilibrium? Okay, so on our graph that you have in front of you, that's the point A. All right, so of course here's where I would ask you somebody to tell me, what do I know is true about point A? I mean, aside from the fact that it is where it returns to equilibrium, I mean a math thing. I need a math thingy to write down. I say, well, you know what? I know at point A, blah, blah, blah is true. And hopefully somebody would tell me that A, at point A, that's where the function crosses the t-axis, or the x-axis, which means, of course, this is a point where the a function is equal to 0, right? That point A right there is A comma 0, right? So I know that the y value, or the u value, is 0. So in order to figure out the mystery of who is this, I'm really just asking, when is this 0? So when is my function 0? Oh, that sounds like an algebra question. So when does it come back to equilibrium? Of course, we know this is synonymous with asking, when is u equal to 0? Well, let's say that. So when is u? Well, u is my whole equation here, right? Let me grab it. So 6 e to the negative 8t cos 8t, and 6 e to the negative 8t sin 8t. Okay, So the time, so this is a when question. So when is it first back to equilibrium? It's at whatever t makes this work. Aha. Okay, so of course the next question is, how do I know what t that is? Well, here's where we have to do just a little bit of algebra / trig, I think, in order to get this answer. Now, of course, if this was just a nice, 0 equals, t plus 7, I mean, I would like that one a lot better, or t minus 7. I'd say, oh, okay, so t equals 7, right? Okay, so, but I do have to do some sort of algebra to make this work. So I got to tell you, these are all going to kind of work like this. So don't worry about, oh my gosh, what kind of crazy scenario am I going to be in when I do these problems? Now, even if you don't have that these numbers, 6 and 6, are the same, you at the very least will have that these numbers, the e thing and the trig thing, you know that they're the same. Because, of course, that's how we got our answer in the first place, right? It's e to the negative at times sine of bt. So those will always match. So what we're about to do will work even if you don't have 6 and 6. Even if you have different numbers up front, this will still work. So let's not overthink this. I'm trying to find out when something is equal to 0. Well, let's immediately make our lives easier by dividing by the e thing, because this has got an e and that's got an e, and 0 divided by anything is 0, and e is certainly not 0. So let's clear out the e's first. That at least makes our lives a little more manageable. And then I just have that, which I still don't know the answer to, but that's a little nicer. Okay, and now from here, I would like to know when this is true. Well, I'm not great at doing trig stuff, I guess, but we do know that inverse trig is helpful. So if I just had that, like I could do inverse cosine and figure this out. But when you have sine and cosine, it's not great. So what you have to do, though, especially because this is what your calculator is going to sort of demand you do, is that if I could write it as tangent, which I know nobody's excited to do right now, but if I could rewrite this involving tangent, I know I have a tan inverse key on my calculator, and so do you. So let's do that. So tangent is sine over cosine, in case you forgot, right? So tangent of whatever is sine of that thing over cosine of that thing. So in this case, if I move cosine to the other side for a brief second here, then if I divide both sides by cosine, you'd have sine of 8t over cosine of 8t, which is exactly tan of, in this case, 8t. Right? So sine of theta over cosine of theta is tan. Now, of course, if I move this 6 to the left, I'd end up with negative 1. Okay, now I claim that this is a moment where we have at least some hope of knowing the answer to this question. But if you don't intuitively know this, which is totally all right, this is, of course, where your calculator is going to be your friend. So I'd like to know what t makes this work. So I encourage you to just sort of come right off over here to the side and say to yourself, first, let's figure out what angle, we like to use theta for our angles, right? What angle does tan equal negative 1? Now that's a tailor-made question for your calculator. And I think you all hopefully remember, right, that if you do tan inverse of, in this case, it's negative 1, because it's that negative 1, that will exactly tell you what theta is. So if I bust out my calculator, make sure you're in radians mode. If I do tan inverse of negative 1, and you type that in, you get a negative number. It's negative 0.78 something. Well, that's unfortunate, because of course that's going to mean that my time is negative. Well, I don't know about you, but I'm pretty sure on my graph, this moment happens at a positive time. Okay, so this is where it's a little, we have to do a little bit of adjustment. So your calculator, of course, like any trig function, there are infinity times when cosine is equal to 1/2, or when tangent is equal to, in this case, negative 1. That happens infinity times. So obviously your calculator can't tell you all of those times, but what it does do is it gives you the one that's basically closest to 0. But of course sometimes that's negative. So when you get a negative number, here, let me write it down. So this is trying to tell us that theta is negative 0.7, I'll just round, 79. It's 785, I think, negative 785. You say, oh, all right, well, that's not quite what I was hoping for. Could you give me the first one that's positive? Because we know that, right? I mean, I'm not telling, right? I mean, this graph, I know that this a value occurs at a positive t. So the way to do this and make your life easy is to remind yourself that tangent repeats every pi radians. So or if you were doing degrees, every 180 degrees, tangent is exactly the same as it was 180 degrees ago, or pi radians ago. So while theta, our calculator says theta is negative 0.79, theta, our fact here is also true if you add any number of pi's that you want. So every pi units, or every pi radians, you get the same answer. And I'm pretty sure if I take that answer and I add pi to it, I'm pretty sure I now have a positive number. 6. We'll call it. Okay, so, I'm sorry, I lost an equal sign there. All right, so here, I'll try to give you a note, right? So tan repeats every pi radians, or units. So if you end up with a positive number, great, right? Then that is the one that you probably wanted. But if you end up with a negative number, it just means that it went a little bit too early. So if you add pi, tan of 2.36, you could check it in your calculator, but tan of 2.36, I promise, is negative 1, or, well, negative 0.99999, or something like that. All right? So if you need to, shift by pi, and that'll get you onto the positive side. But here's where I shouldn't circle that, because now I come back to my original question, which said, could you tell me what t makes this true? Well, we found out that the angle you want is 2.36. Now that's not t, though. That's 8t. So I have to do one last step. I'm just going to do it over here in the corner. So, all right. So I did answer this question, but I answered a side question. But I have to translate back now and say, okay, so 8t, that's what needs to be 2.36. Oh, okay, so t, I divide by 8, it tells me is about 0.3, I'm just going to actually round that to 0.3. It's 0.295. No, okay, I'm just going to call that 0.3 since, oh, maybe I shouldn't do that. Okay, so maybe I'll do, go 295. Okay, just for, so after about 0.3 seconds, is when, which again in real life, I don't know, I mean, spring moves pretty darn quick, right? 0.3 seconds, that's almost sort of instant. So this is probably a very firm spring. It doesn't have a whole lot of elasticity, and it also has a fair amount of drag or damping on it. So it's going to sort of move reasonably quickly down towards equilibrium. So it only takes about 0.3 or so seconds. So this point right here is 0.295, 0. All right. So that's the A, which is a kind of an important moment. I think some of the homework questions ask you to figure out when it first returns to equilibrium. So you want to do something like this. All right. Let's answer the second one, and then we'll call this video. So the second point here is asking in either picture. How about when it maybe reaches what I think the book calls a very funny, I think it's a very funny name. It's extreme displacement, or its most extreme displacement. I don't know, something about the word extreme makes me think that it's like wild and crazy or somehow, well, anyway. But B here, this point B, we can see, right, this is the point where it comes closest to the ceiling. Or if I was talking about U, this would be the point where it's the furthest below the t-axis here, is this B moment. So I'll phrase this on a clean slide in a second. But once again, just like I would have asked about, hey, somebody tell me something famous about A. If I asked somebody to tell me something famous about B, I'm hoping somebody would say, oh, B, That's what in Calc 1 we called a local minimum, or at the very least, we would hopefully agree that B is where the slope is 0. And in fact, it's the first time that the slope is 0. So I think if I'm going to try to say, how do I figure out B? So let me pose this to you. So I'll ask this the way the book does. When does the ball have its most extreme displacement after equilibrium? Is usually clarified if need be. In other words, 6, which is the starting point, that's actually the most extreme displacement from equilibrium. But usually it says after returning to equilibrium. Oh, sorry, after returning to equilibrium. In other words, the rebound. Okay, so which bounce is the biggest, and what is it, probably, right? So it's talking about this B moment, all right? So it wants to know where, okay. So, okay, well, I think this B moment, this is really asking, when is the derivative 0? Right? That would tell me when the graph is flat, which is exactly this B moment that we're looking for. Okay, so this is almost the same as what we did in part A. In part A, I set u equal to 0, but in part B here, I'm going to set u prime equal to 0. All right? So at least that's what I would do. Oh, that's right. I'm going to chicken out on this problem because I don't want to do... Okay, right. In theory, this is what I would do, right? Is I would take, here's u, and if I compute u prime, the derivative of that, if I set it equal to 0, I could do a similar trick like we did here to solve for u. Now, I'm saying that very casually, and maybe you're on to my shenanigans. Okay, it gets a little bit messy, right? Because you just got a lot of pieces here. So, I will first of all tell you the thing you care about the most. No, I'm not going to ask you to solve something that awful. But would I ask you to do this question on a problem for which the math isn't so bad, and it more or less is as easy as doing the math in part A? Of course. And I am going to do an example where I do answer that question in the next model, which will be in the next video. So I'm just going to write a sentence or two here. So this is equivalent to this. So of course we would take the derivative of u, set it equal to 0, and do a similar trick. To what we did in part A. Right? This is just a little bit awful because you end up with 4 pieces, because each of these is a product rule. All right, but you know, you get some stuff with cosines, you get some stuff with sines, and you sort of put them together in the same way. You put them both on one side and make it into a tan, and then you're good to go. But this is pretty awful and ugly, so let's not do that. Right? But that's the idea of this. Right? Okay, so one example done. And this is an example, maybe I'll label it here on the graph. This is an example of what in physics is usually known as under-dampened vibration. Oop, can I fit that in? Under, meaning that that the vibration eventually ends, I guess, is which is going to be true in all of these. So these terms are not important. I don't care, and I'm not going to ask you about them. But And I don't even think they really use them in any of the homework problems, but just sort of FYI. But this is one type of graph. What I wanted to say is this is one type of graph that we're going to have, which is one where, there's bouncing, but then it eventually dies out. The next example we're going to look at is where we have bouncing, but it doesn't eventually die out, which we're going to have to think a little bit about what the heck does that mean, and answer some follow-up questions on that. And then a third example, which is actually from an engineering and design perspective, is what's known as the critically dampened vibration, is the sweet spot. This is the mechanic's dream of how you'd want to actually design things that are going to vibrate if you want them to vibrate sort of harmoniously, I guess, is the best way to say that. So we'll do 2 more examples. Those I'll probably maybe do all in one video since I'll go a little quicker through those 2. Similar questions, similar setup, and discuss the graphs and all of that good stuff too. So stay tuned for a couple more examples, but I've shown you at least, the general idea, I think, of how to do any of these, so you're certainly welcome to get started into problems, or keep watching if you want to see a few more examples before trying them yourself.